Okay, so welcome to our last talk, and our speaker is Ariel Rapaport from Technion, Israel, and his title is Dimension of Self-Conformal Measures on C associated to an exponentially separated holomorphic IFS. So please, Ariel.
Yes, thanks a lot. Yeah, thank you to Antti and Chacha for inviting me to speak. And so what I'm going to talk about is this is joint work with Zhao Feng, which is currently a postdoc at the Technion. So I'll start with some general background about what I'm relevant to the talk, and later on I will be more precise when I reach the precise setup in which we obtain our main result. So let phi be a conformal iterated function system on RD. So what I mean by this is a finite collection of conformal contractions of a bounded domain in RD with some additional mild and standard assumption that later on I will specify. And let P be a positive probability vector indexed with the same index set, and let mu denote the self-conformal measure associated to phi and p. So this mu, this is the unique Borel probability measure which satisfies this relation. This is the push forward of mu via phi I. So this is the unique stationary measure associated with the random walk induced by phi and p. I mean the random walk that goes from point x to phi ix with probability pi. And let us write k phi for the support of mu, which is simply the self-conformal set associated to phi. By a result of De Feng and Hui Hu from 2009, mu is known to be exact dimensional, which means that there exists a number d mu, denoted d mu, such that for mu almost every x, this limit exists and is equal to the same number d mu. So this is the closed ball with center x and radius delta. And yeah, so in this talk, I'm interested in this. The research presented in this talk about this is about the computation of this value of the dimension. So I'll say that we say that phi satisfies the strong separation condition, or SSC for short, if the images of the self-conformal set with respect to the maps in the IFS are disjoint. So this is kind of the simplest situation to analyze, and in this case it is easy to show that the dimension satisfies this nice formula. So D here, this is the dimension of the ambient space. This is the entropy of P. This is the Lyapunov exponent associated to phi and P. Later on, I'll define this precisely. And so under the strong separation condition, this formula, which I denote by 1, is easy to establish. Another thing that is easy to show that always the right-hand side, regardless of any separation assumption, the right-hand side is always an upper bound for the dimension. And moreover, for many, I'm being a little vague here, but for many parameterized families of conformal iterated function systems, the above equality holds for almost every choice of parameters. This, for instance, is shown in the results of Shimon, Solomiak, and Urbansky in dimension 1, and in the Hunt in higher dimensions. Given this, it is natural natural to look for explicit conditions that ensuring this equality one that are much milder than the restrictive strong separation condition. So we have this value on the right hand side of 1, which is by these results, for instance, show that this is kind of the correct value for the dimension, and this is indeed the value in the most simplest situation, in the simplest situation of the strong separation condition. And it is a natural and important problem in this area to look for conditions which are much milder, or even as mild as possible, for the validity of this equality. So in 2014, Hochmann made an important breakthrough on this and showed that the equality, which I denoted by 1, holds in the self-similar case on R under the exponential separation condition, or ESC for short. So the self-similar case, I mean when all of the maps in the IFS are contracting similarities. And later on, under additional necessary assumptions, he extended this to higher dimensional to the higher dimensional self-similar case. So in higher dimension, there are some phenomena, some obvious, some less obvious, that may prevent. That it prevent the validity of this equality, and then in a suitable theorem for establishing this equality, you need to rule these things out. I will later go back to it, to these phenomena that occur in higher dimensions. And recently I established one in the real analytic case on R under the exponential separation condition, which means basically I extended Hochmann's result from self-similar measures on R to stationary measures associated to real analytic IFSs, which satisfy the exponential separation condition. So, for instance, if the maps are polynomial, then this is falls under this case. And given these results, it is a natural next step to consider the above equality in the context of exponentially separated holomorphic iterated functions on C, which is the purpose of this talk. So in general, it is natural, of course, to try to extend, given this last result in the real analytic case on R, it is natural to try to extend Hochmann's work to the conformal case in higher dimensions. But in dimension 3 and in higher, the situation is quite different and actually easier in a certain sense, because then you look at all of the maps that are the conformal maps form a finite dimensional Lie group, which is make the situation kind of simpler and different. And the most I would say next step, the immediate extension of this to higher dimension would be the holomorphic case, which I'm going to discuss in this talk. Okay, now for the basic setup, and I'm going to start being more precise. So throughout the talk, let omega be a bounded domain in C, simply a bounded, open, connected, non-empty subset of C. And let lambda be a finite index set. And for each I, let phi I be a map from the closure of omega into omega. And I will also always assume the following two kind of standard assumptions. First, that there exists a domain omega tag containing omega prime containing the closure of omega, such that for every I in lambda, the map phi I extends to a holomorphic injection on this larger domain omega prime. The second assumption that for every I and for every Z in the closure of omega, the modulus of the derivative of phi I at the point Z is bounded away from 0 and 1. Then writing phi for this collection of maps, for this the index collection of maps, the collection phi is commonly referred to as the holomorphic IFS on omega. And it will also be convenient to have the following notation. Let K phi denote the self-conformal set associated to phi, which means that K phi is the unique non-empty compact subset of omega, which satisfies this relation. That the unique compact non-empty subset of omega, which is equal to the union of its own images with respect to the maps in the IFS. Okay, but I'm interested in measures, in the dimension of measures in this talk. So let P be a positive probability vector, and let also indexed by lambda, and let mu denote the self-conformal measure associated to phi and P. Again, this simply means that mu is the unique Borel probability measure on omega, which satisfies this relation. And don't note that since the coordinate the P is strictly positive, support of mu are precisely equal to the attractor, to the self-conformal state. And let us write the HP for the entropy of P and chi for the Lyapunov exponent associated to phi and P, which are defined as follows. So this, the entropy of P is defined by this well-known formula, and the Lyapunov exponent is defined like this. So the Lyapunov exponent is a positive number which quantifies the average contraction rate of the system, and the entropy quantifies how mass is distributed within the systems within the system, and yes. So as I said before, our goal is to establish this formula. Now 2 appears here because the real dimension of the ambient space is 2. So our goal is to establish this formula under assumptions as mild as possible. Okay, let me move on to possible obstructions. So in what follows, I list several obstructions to the validity of the above equality, this equality, which are again referred to as 1. So I'll list several obstructions to the validity of this equality that must be ruled out. There are kind of obvious things that could prevent one from holding, and then in a theorem verifying this equality, you need to rule them out explicitly. So first of all, the most trivial one is that everything collapses to a single point. So to a single point. So first, note that if the maps in phi have a common fixed point, then the attractor is a singleton. And in this situation, the above equality clearly fails unless the system consists of a single map. Right? If this is a singleton, then the mu is a mass point, and then it's zero dimensional, and then the right hand side is zero dimensional only if this happens, if we are talking about a system of a single map. So this case must be ruled out explicitly. This is kind of the first and most obvious obstruction. Second obstruction, a little bit more interesting, is that of an invariant curve. Let me be precise about this. So I'll say that we say that gamma in C is a regular real analytic curve if it is an embedded one-dimensional real analytic submanifold of C. Or what this means, that for every Z not in gamma, there exists an open subset U of C, an open interval J of R, and a real analytic map small gamma from J into C, such that the image of this map is precisely big gamma intersected with U. Gamma is a homeomorphism onto its image, and the derivative at each point is non-zero. So it's simply a regular real analytic curve is simply an embedded one-dimensional submanifold of C with the additional assumption that the charts, the coordinate maps are real analytic. Now, assuming that gamma is contained in omega, I'll say that gamma is phi invariant if it is invariant under all of the maps in phi. For every I, phi I maps gamma into itself. Now, clearly, being a one-dimensional manifold, the Hausdorff dimension of gamma is equal to 1. And from this, and since the dimension of mu is bounded above by the dimension of the attractor, it follows that the equality that we are interested in fails whenever the attractor is contained in gamma, and also the ratio of the entropy divided by exponent is strictly larger than 1, right? Because in this, if this happens, the dimension of mu, given this, the dimension of mu is at most 1, and the right hand side, the minimum between two of this, and will be greater than 1, and so we cannot have equality. Also note that the attractor is always contained in gamma whenever gamma is phi invariant and closed, and is a closed subset of omega, where omega is equipped with the subspace topology. And so given this, so this of course this is an easy exercise, and given this, it is necessary to assume that if one wants to establish this equality denoted 1 in general, it is necessary to assume that there does not exist a regular real analytic curve gamma, which is phi invariant and is a closed subset of omega. This was the second obstruction. Third obstruction is conjugacy to a homothetic IFS. So given an open subset U of C, a function from U into C is said to be a homothetic if it is an affine map of C whose contraction is a non-zero real number. So a function of this form, if it has a restriction of a function of this form, where the contraction is a non-zero real number. So by an example of Hochmann appearing in his RD paper, the equality which I do not the equality that we are interested in may fail when the maps when all of the maps in phi are homothetic. So let me elaborate in this a little bit. So he constructed a relatively simple example in which all of the necessary things happen. I mean, the system, the maps do not have a common fixed point. They do not, there is no line which is, these are examples in the plane. So there is no affine line which is invariant with respect to all of the maps. And so there is no curve which is invariant. The maps, I mean, this is in the self-similar case. And also the system is exponentially separated. I still did not define exponential separation, but soon I will do it precisely. Everything is okay, but still there is dimension drop. And what goes wrong in these systems that the measure, the stationary, the corresponding stationary measure, it is kind of saturated along certain lines. It has full dimension or entropy along these lines, but it does not have full measure in full dimension in general. And then but it kind of wants to have more dimension on the line on which it is saturated, but it is already full, so there is no room for more dimension, and then you have dimension drop. This was a bit imprecise, but this is the intuition for what is happening. But the point is that this kind of example only happen when we are dealing when one deals with, I mean, in the self-similar case, they only happen when one deals with homothetic systems consisting only of homothéses. So this is something, and we don't have, it doesn't seem to, we don't seem to have a, there does not seem to be a nice condition within the homothetic case that prevents this from happening. So, so the homothetic case is something to avoid if one wants to verify the Formula 1. But in the setup we're considering here, we need to avoid something a bit more general. Since conjugation does not affect dimension, we want to avoid the situation in which one can conjugate the system into a self-homothetic system. So let me define this precisely. So we say that phi is holomorphically conjugate to a homothetic IFS if there exists a holomorphic and injective map psi. So this, note that such a map is B holomorphic. I mean, its inverse is also holomorphic, such that the conjugation of phi I by this map is homothetic for every I in lambda. So this is what I'll refer to as being holomorphically conjugate to a homothetic IFS. And note that the push forward of mu via psi is precisely the self-conformal measure associated to P and the conjugated system. So and then of course the dimension properties of this push forward and of mu are the same. And so if this measure experiences the dimension drop, then also mu experiences the dimension drop. And so we need to avoid the situation in which this system is homothetic. Yeah. So consequently, it is necessary to assume that phi is not holomorphically conjugate to a homothetic IFS. Okay, the fourth and last obstruction is that of exact overlaps. Given a word u, I write phi u, a word u over lambda, I write u for the corresponding compositions of maps from the IFS. And we say that phi has exact overlaps if there exist distinct words over lambda, u1 and u2, such that the corresponding compositions are the same. Or equivalently, phi has exact overlaps if it does not generate a free semigroup. Now it is easy to show that when phi has exact overlaps, there exists a holomorphic IFS phi prime and a probability vector p prime such that mu is generated also by by phi prime and p prime. The Lyapunov exponent associated to phi prime and p prime is the same as the original Lyapunov exponent associated to phi and p, but the probability vector associated to phi prime is strictly less but the entropy associated to this to p prime, to the new probability vector, is strictly less than the entropy of the old probability vector. For instance, consider the case that you have a system in which the same map appears once, then you can join the two maps into one and join the two coordinates in the probability vector, and then you will get this situation. In any case, in this case, the dimension of mu will also always be bounded by this. This is the usual upper bound, right? The right-hand side is always an upper bound in the equality that I denoted by 1, and I'm applying this to the system, to the weighted system phi prime p prime, and then we get this inequality. But we have this inequality and this equality, and then we have here strong equality, and we have and also and always in the presence of exact overlaps, it always holds that the entropy of p divided by exponent is strictly more than the dimension of mu. And so the equality that you are interested in will fail whenever phi has exact overlaps, but the dimension of mu is strictly less than 2. Right, because then the right hand side will be, it will be just this is more than d mu and this is more than d mu, and the right hand side is the minimum of these two quantities, and we do not have equality in one. And so it is necessary to assume in general, if you are interested in the verifying one, that phi has no exact overlaps. Okay, this is a good moment to talk about the exponential separation condition. So unfortunately, we are unable to establish the equality one with the only separation assumption being the absence of exact overlaps. Indeed, such a statement has not been established even for self-similar measures on R. In the much simpler case, probably of self-similar measures on R, in which case the validity of this statement is a major open problem in fractal geometry. So the validity of this statement in the self-similar case on R is the commonly called the exact overlap conjecture, which is a big open question in fractal geometry, and it is not verified in the much simpler case of self-similar measures on the line, and we cannot expect to solve it in this harder case of this more complicated general holomorphic case. And so we need the following separation condition, which was introduced by Hochmann in his work on the self-similar case. And for this, let the norm omega denote the supremum norm on omega, which is defined, of course, as follows. For a bounded function for omega to c, it is simply defined like this. And now I can define exponential separation. So we say that the system phi is exponentially separated if there exists a positive constant small c, such that for infinitely many positive integer, for infinitely many positive integers n, for all distinct n words u1 and u2, the distance between the corresponding compositions with respect to this norm is at least c to the power n. Okay, this is exponential separation. It implies the absence of exact overlap, but it is quite a mild, it is an extremely mild separation condition. In particular, this sequence on which this happens, it is required that there are infinitely many n, but the sequence when this happens could be extremely sparse. Okay, now I can finally state the main result. So as I said, this is joint work with Zhao Feng, and our result says the following. So let omega be a bounded domain, and let a bounded domain in C, and let phi be a holomorphic IFS on omega. So recall, this is just an IFS, a collection of maps phi I, which satisfy these two conditions I stated when I began to describing our setup. So they could be extended to a holomorphic injection slightly beyond the closure of omega, and also the derivative at each point of omega closure is of modulus strictly between 0 and 1. This is what the holomorphic IFS means. And also I assume that all of the obstructions I described do not happen, and also the system is exponentially separated, and then we get what we want. This is the theorem, so let me state it precisely. So suppose further that the maps in phi do not have a common fixed point. There does not exist a regular real analytic curve gamma contained in omega, which is phi invariant and closed in omega. And assume also that phi is not holomorphically conjugate to a homothetic IFS, and also assume that phi is exponentially separated. Then if all of this happens, then for every positive probability vector P indexed by lambda, the dimension of mu satisfies the nice formula, where mu is the self-conformal measure associated to phi and P. So as I said in the previous discussion, first three conditions are basically necessary. The fourth condition, we would have an optimal result would have been to replace the fourth condition with the absence of exact overlap, but given the exact overlap conjecture is open and hard, even open and seem very hard even in the self-similar case. This is kind of at present the best we can do. Okay. I guess not the best. There is probably room for much more research. Like also the exact overlap conjecture, there have been much progress in recent years. But yeah, but in general, we cannot expect to resolve the conjecture in this more complicated holomorphic setup. Okay, let me say a couple of remarks on this theorem. So first of all, I will not get into it, but it's of course possible to use the theorem in order to compute the Hausdorff dimension of the attractor. And let me say another remark is about the validity of these two conditions, 2 and 3. So on a first glance, it seems that it seemed maybe hard, difficult to verify them, to establish that there is no curve which is invariant and no system which is no homothetic system which is conjugate to our system, but actually there is a condition that seems quite mild and implies these two conditions together. Let me state it. So given a word u, write zu for the unique fixed point of the map phi u. And then it is easy to see that it is an easy exercise to show that the condition 2 and 3 hold whenever there exists a word u such that the derivative of phi u at its fixed point is not a real number. Right? This thing prevents from an invariant curve from existing and from and also from a conjugating a homothetic system. It is not difficult to show this, and then it should help in applications to verify conditions 2 and 3. Right, if we're dealing, let's say, with quadratic polynomial, then computing the fixed point is easy, and then maybe verifying this is easy. I mean, at least for the maps in the IFS, and could be a good way to verify these conditions. Related to explicit examples, so Balash Barani, Ishtovan Kolosvari, and Sacha Trushiet recently constructed explicit examples of overlapping exponentially separated real analytic IFSs on R, and then use this and also combine my recent result on the real analytic case to get new example of overlapping systems for which the desired formula holds, and extending their results to the holomorphic setting, which seems like an interesting thing to try, that should, I get, with a good chance of working. So extending the result to the holomorphic setting discussed here and applying our main theorem will yield new overlapping examples for which the desired equality holds. Final remark regarding parametric families. So combining our theorem with a result of Boris Solomiak and Yuki Takahashi, it follows that under mild assumptions, given a one-parameter family of holomorphic IFSs, the set of parameters for which the equality we're interested in fails has zero Hausdorff dimension. So a result combined with a result of Solomiak and Takahashi gives strong result for parametric family. So in the beginning of the talk, I recalled some relatively old results on parametric families in which the exceptional set, I mean the kind of the bad set in which the equality does not happen, is of zero Lebesgue measure. And here we, with our result and this result of Solomiak and Takahashi, we're able to improve it to improve it so that the exceptional set is of zero Hausdorff dimension, which is of course a big improvement. Yeah, so I'm out of time, so maybe I should stop here. Whatever. Antti and Sacha tell me?
Uh, well, personally, I would of course be interested in listening to details about the proof, but let's follow the schedule. So, yeah, so thank you very much at first for a very nice talk. And are there any questions, comments?
Can you say something about the proof?
Yes, of course.
Yeah, that's excellent question. Thank you, Sasha.
Thank you for the
So
question.
please,
Yes.
Ariel.
Yeah, so a little bit about the proof. So the following entropy increase result plays a major role in the proof of our main theorem. I need for this some notation. So as in many important developments in recent years in this business of dimensional stationary measure, there is an entropy increase, a result that guarantees entropy increase that plays a major role. And let me talk a little bit about this and how it blends in the proof. So for this, a little bit more notation. So given k, write pk for the vector space of polynomials with complex coefficients with degree at most k. And in what follows, I'll identify pk with this space with c to the power k plus 1 as complex normed vector spaces in a natural way. So this is equipped with the standard norm, and the identification is what you think. It takes a polynomial to the vector of its coefficients, right? And then all metric properties and dyadic partitions and so on. And then the norm, I'm bringing it here from here to here, okay, in what follows. And also let mu again be a self-conformal measure of mu, which again satisfies all of the conditions of the main theorem. And now our entropy increase result says the following. It is entropy increase result for convolutions with measures on this space of polynomials. So first of all, we need to assume that the dimension, in order to get entropy increase, we need to assume this, because if dimension is full, there is no room to grow, no room for more entropy, and so this need to be assumed. And also, if this does not happen, if the dimension of mu is equal to 2, then there is nothing to prove in the main result. Then under this assumption, for every positive integer k and for every epsilon strictly between 0 and 1, there exists a number rho depending on k and epsilon, such that the following holds for all sufficiently large n depending also on k and epsilon. So let nu be a compactly supported Borel probability measure on the space of polynomials, and suppose that for every q in its support, its norm, again, I'm bringing the norm from this space, the norm is bounded like by this, by epsilon to the minus 1, and the derivative is bounded away from 0 like this for every point in omega. And also assume that the measure has non-negligible entropy. In this sense, its normalized entropy at scale n is at least epsilon. So again, these are dyadic partition when the partition, natural dyadic partition from here are imported to here. Then under these conditions, the normalized entropy of the convolution of nu and mu is at least as large as the dimension of mu plus rho. So again, this notation nu dot mu is simply the convolution of nu and mu, the push forward of the product measure via the action map. And I'm saying that I refer to it as an entropy increase result because recall that mu is exact dimensional, and then the dimension of mu is very close to is arbitrarily close as n is large for large n, it is very close to the normalized entropy of mu alone. So formally, I would get the same statement if I write here normalized n entropy of mu alone. So to sum it up, the theorem guarantees increase in entropy, substantial increase in entropy when convolving with a measure on the space of polynomials. If this is okay, I will say a little bit more about what's going on in the proof.
Yes, please. Yes.
Yes, yes. Okay, thank you. So the proof of our main theorem consists now, given I stated this entropy increase result, the proof of our main theorem consists of two, roughly speaking, it consists of two major parts. The first part is proving the entropy increase result. Second part is using this entropy increase result in order to derive the main theorem. So the novelty of this work lies in the first part. Let me say a little bit about the second part. So the second part, I mean, deriving the main result from the entropy increase result. This is a modification of an argument that appear in my recent work on the real analytic case on R. And this argument basically enables one to reduce convolutions of mu with measures on the infinite dimensional space of holomorphic maps to convolutions with measures on these finite dimensional vector spaces. And the advantage of reducing to the convolutions of these spaces is precisely that one is able to establish this entropy increase result. I have no idea if this is true or possible to establish or even how to precisely state it, an entropy increase result for these spaces of holomorphic maps, but here it works. But here, yeah, so being able to establish the entropy increase result, this is the reason for approximating convolutions on the space of holomorphic maps to convolutions with measures that sit here. And yeah, this is the last slide, and I'll end the description of the proof, which we're talking a little bit about the first part. I mean, proving the entropy increase result, which is the main novelty of this work. So in the first part, when we establish the entropy increase result, the main challenge is showing that under the assumptions of the theorem, there exists a positive gamma such that for every sufficiently large n, for most integers n, I mean most integers between most scales n, between 1 and some huge number big N, and most n components theta of mu. So an n component, this is an n component, a conditioning of mu on a dyadic cell. So again, for every sufficiently large m, most integers between some most scales n and most n components theta, for every line, so every line, this is a real projective space of C, for every one-dimensional real subspace of C, the normalized entropy of the orthogonal projection of the component is bounded away from, it satisfies this lower bound. So the point is that establishing a similar statement with gamma removed, or let's say gamma replaced with an arbitrarily small epsilon, this is an easy thing to do, but it will be completely useless for proving the entropy increase result. We need, in order for the entropy increase result, precisely we need this small improvement for the entropy of projections. Why, right? The correct value on given by, I don't know, for the expected value is kind of that for every direction, the dimension will be, right, the value given by Marstrand's theorem, the minimum between 1 and the dimension of mu. But we have no idea how to prove this. Instead, we get this small improvement, which is precisely what is necessary for the entropy increase result, because it prevents this phenomenon of saturation. If saturation of components, this is kind of the major enemy in proving the entropy increase result. And if you have this uniform lower bound at the dimension of orthogonal projection, you cannot be saturated. The dimension of components, the entropy of component will be too much. Yes, so just one last remark. So the proof of this thing with this statement about projection, it extends an ergodic theoretic argument, and the extended ergodic theoretic argument, which appears in a recent joint work I have with Hao-Ji Ren, which is also a postdoc at the Technion, on the dimension of Furstenberg measures on CP1. And this extension, it involves some complex analytic tools, some complex analytic tool play a part in a nice way, and this is kind of the main novelty of this work. So in both of these cases, there is a natural cocycle that comes into play when you want to prove such a statement, and this statement boils down to proving that this cocycle is not trivial, that it's not a co-boundary, and for this we need this ergodic theoretic tool. That's it. Thank you, and I hope I didn't go too much beyond the time.
Okay, thank you.